And let me change my camera. That's not going to focus because I've not written anything. We've got cross sections. And cylindrical shells. Are there two L's in cylinder? I forget English, guys. You do math for too long. And like, I don't know how things are spelled. Are there two L's? Asymptote. I did this last summer. The word asymptote apparently only has one S, and I was putting two S's in it because I think I see the word assignment, which has two S's in it. And then
No, it's one L.
one L. Yeah, that's what I first thought, but then it didn't look right, you know. Okay, so cross-sectional volumes and cylindrical shells. So cross sections, let's try to find, so find the volume of a pyramid. We'll say with, let's give it a base. Give it actual numbers. Base widths of, let's say 6, height 9, and then I guess I should say a square base. Can you guys see that? Is it focusing well? There you go. So let's draw a picture. So we've got some pyramid. Base is 6. Height is 9. And we've got this kind of these square base. So the sort of cross section I drew was kind of like there in the middle. And so maybe we have the kind of the square base coming out front. So something like that. And so, well, how do we find a volume of something like this? It's not a rotation, right? It doesn't have any sort of axis of symmetry or anything like that in terms of rotation, but we do have a nice square base. And what you can kind of imagine is if I cut it horizontally, so if we take out a horizontal slice, should be a square. Because of the symmetry of everything, because the base is symmetric and we assume that kind of the axis is going up through the center, it's not like a skewed pyramid to one side or another or anything like that. Cross section is a square, and the height, so to speak, of these cross sections is dy. What we need to do is to model the side length. Of the cross section. So this problem is a little bit more in depth than a lot of these other cross-sectional problems because we're just given an abstract shape. We actually need to come up with the equations ourselves. And once we do so, should be pretty straightforward from that. So let's kind of pick out the center again. So the width, so if this is the center of the cross section going right through the middle, then of course the width is just going to be 2x. So let me draw a new picture for that and kind of pick that out. So this is kind of like just the center through it, and our cross sections are going to be cut this way. And well, if this is my y-axis, then of course half the width is just x. Of course, this is a little problematic because our cross sections have a width of dy. So really what we need is to model these functions. And how do we come up with that? Hopefully it's kind of popping out at everyone. Kind of a basic pre-calc exercise to just come up with equations of lines, right? So the entire width at the base was 6. So I know I'm going to have 3 on this side. In other words, let's actually give it coordinates. So it's going to be 3 on the x-axis. And of course, the height goes up to 6 on the y-axis. So how do I model this line? Well, we could use point slope. So our slope is I go down 6, right 3. So slope is -2. And the equation of our line is y equals -2.
Height is 9, right?
What did you say?
Height is 9, not 6.
Oh, did I change my numbers around? Yeah,
Yeah.
9. Sorry about that. Height is 9. So our slope is -3. And in this case, since we know the y-intercept is 9, of course, we can just use point slope. So y equals mx plus b is the equation for that line. What's the equation of this line? Should just be +3 going on. So check that slope on your own, of course. We're now just going right 3, up 9. So +3 slope, same y-intercept. Let that focus for a second. Okay, so, well, what is the width? If the width of each box, of each cross section is 2x, or you could model it as the distance between these two curves. Kind of need to organize my work a little bit. We should probably solve each of these lines in terms of x because we need everything, our functions, in terms of y. So the first function, what do we get? We'll have y -9 all over -3. And x equals y -9 all over +3 for the other one. So the width you could either model as 2x and use x as this line, or you can model as the right curve minus the left curve. So if you model the entire width of any given cross section as the right minus the left, it'll give me that distance going across. And in either case, we will get the width is, so essentially twice x, so it'll just be 2 times, I'm going to go ahead and change that, 9 minus y, just to get the minus sign up, over 3. And of course, if I did right minus the left, we'd get the exact same thing. And so now to set up our equation, so I might have to pull that paper back to just to give all the pictures there. Or I can just redraw stuff, I guess. Let's just redraw it. So if our width was 2 times 9 minus y over 3, I know that the height of each box is a dy, and then of course the area is then w squared times the height. And this is of course because each of our cross sections were squares. So we found the width just by sort of measuring across the middle of one of the squares. Of course, that's the same as the depth. So that'll give me a w squared times the dy. So all in all, what do we get for the area? Actually, I guess I should call this volume, actually, since I'm including the third dimension, the dy. It'll be 2/3 9 minus y, all of that squared, times dy. And now all we got to do is integrate all that. And actually, you know what? Let me introduce a little bit different notation. I have this called as volume. Let me actually call this dV. So what do I mean by dV? Well, because this isn't the total volume, right? This is just the infinitesimal volume of our cross-sectional square. I like to kind of write these types of things just because it helps me organize my thought process and where I'm at and keep that set up between where I'm at in any of these problems. So I'm going to start using this notation a little bit more, and I hope it kind of catches on. It's really useful for work problems as well, once we start to get into those at the end of this week, where you kind of just think, well, what is the volume? Generically, volume is the integral of all the infinitesimal pieces of volume. That's all we really need. And by the way we're slicing it up, what's that going to be? It's just going to be the width squared times the infinitesimal change in height. So this is kind of another way to just organize your thought process of, well, what is the infinitesimal piece we have? Well, we're cutting up these infinitesimal little volumes, adding them all up in an integral. And well, by the way we're slicing, the sort of smallest side, the infinitesimally thin side, is just the height, the dy. And then so this is kind of a nice way to even start the problem and just set it up. And then you can kind of go back and think, okay, now I just need to solve for what is this width? So I kind of started off the problem knowing ahead that that's what we needed to solve for, these widths. But if you're ever kind of confused in any of these general volume problems, you can kind of just basically draw a picture and start off with this type of generic thought process. And then you can kind of think, use your problem solving. Okay, now I need to solve for W. And it's kind of a nice way to break the problem down and keep your thoughts organized. Okay, so we found our W, and so now what is our volume? I'm going to go ahead and square that constant. So 4/9 9 minus y, quantity squared, dy. And then what are the bounds of integration? So we were integrating dy's, go from 0 up to 9. Okay, so let's actually just go ahead and finish this guy. A lot of these integrals I don't want to finish just because I think you guys are comfortable with doing these. But this one was a generic geometric problem. We didn't actually have formulas originally given to us. And there is a well-known formula for the volume of a pyramid, which might have come up in Calc 1 a few times if you guys took Calc 1 with us. So what do we got to do? Let's square everything out and then just integrate. So I'm going to go through that a little quick. We've got 9 squared is 81 minus 18y plus y squared dy. We will have 4/9 81y minus 9y squared plus 1/3 y cubed. Evaluating between 0 and 9. 0 doesn't matter. When I plug in the 9, not even going to multiply things out just because I don't want to do 9 times 81. I can just write it as 81 times 9 minus, again, we'll have a 9 times 81 plus 1/3 9 cubed. So sometimes it's nice to just keep things factored. One, because we have these divisors, these powers of 9 in the denominator that we can cancel out. And as well, this kind of worked out nicely where these two terms are exactly the same and just subtracting each other. And so what do we get? It looks like I have 4/3 9 squared. So that's going to be 4 times 81 over 3, which is 4 times 27. And then what is that? So that's what, 80 plus 28. So 108. Oop, going off the page there. And then, of course, the units, I don't know, let's say we were in meters or feet. I didn't specify it at the beginning what the dimensions were, at least in terms of the units. Let's say meters cubed. Anyone know the formula for these guys? For pyramids? The volume formula? We can check it real quick. So, well, you kind of think a pyramid, it's a square base. It fits inside of a rectangular prism. So the volume should be something like the base, or let's write it as the length times the width times the height will give me a rectangular prism. And then for pyramids, the constant that kind of just goes that makes it a pyramid is 1/3 of that. And so in this case, what would that have given us? 1/3 length times width were both the same. They were both 6, right? So 6 squared times 9. So that gives us 6 squared times 3, which is 6 squared is what, 36 times 3, which gives, so 3 times 3, 90 plus 18, 108. So we came up with the correct formula. And if you guys wanted to, so I gave specific dimensions in terms of the base and width. If we wanted to, we could have just kept the base as B and the height as H. We would have had some sort of dummy variables in there, but we could have gone through the same process and hopefully re-derived the exact formula that we needed for the volume of a pyramid. Any questions on that? So we'll take a look at one of the ones on your homework. I think one of the last one. It's actually pretty tricky. If you're just given a geometric shape, especially a 3D shape, and you're asked to find a volume of it, it's kind of hard. This one wasn't too bad because it was pretty clear that because the base was square, if I cut it horizontally, those shapes that would have been resulted from those slices are square. It would have maintained its square shape just with a changing width. And so all we had to do was figure out that changing width, the function that modeled that. It can be a little tricky though if you're given a wonky shape, like you are in this homework problem, of how do I slice this thing up and what is the appropriate way to slice it? If you kind of misthink of it, or if you don't have, the correct visual spatial representation in your brain, you can kind of easily confuse some things. We'll come back to that though. So let's do, actually what I wanted to do with the rest of these cross sections, there's an activity for today. So if you guys could go ahead and pull up the website. I don't want to do this. I don't want to assign groups because it's fairly short. It's only like 5 problems. So why don't we kind of just go over it together? I'll just kind of talk them out and go through it if you guys want to follow along. So either pull up the schedule and then look for today, June 16th, and click on that activity, the green activity, solids with known cross sections, and it'll pull it up. Or if you want to find it, click on the projects section, and then you should be able to find that as well. It's kind of hard. They don't have the website organized too well. It's at least for summer, because it's not organized by week, because the weeks in our summer are different from fall and spring. There it is. So it's kind of like 2/3 of the way down in that first section. It says activity, finding the volumes of solids with known cross sections. So pick that out. It's kind of, use your own scratch paper. They give you a little graph, but there's no way, even if I was able to give this to you as a handout, that those graphs are big enough to draw on to get some of these shapes out. So the first one says the base is a circle of radius 2. Centered about the origin, cross sections perpendicular to x-axis. Are squares. So sorry, I wasn't on the video there. I was looking at at that sheet on the website. So first step with almost all these, draw a picture. And all we want to do for this problem is just set up the integral. Since you've learned all the techniques of integration now, they're just now going to keep coming up. They're going to keep being applied with all of these situations. So if any of them are difficult or look like it's going to be a little fancy to do the integral and you guys want me to do it, let me know. I think with most of these though, since a lot of the functions are just polynomials, once you set up the integral, doing it is fairly straightforward. So we've got radius of 2, and we've got a circle. And then, so cross sections, what do we need to know about the cross sections? We need to know the direction they're going and the shape. 2 key things. The last one, we had to figure that out ourselves. This one, they essentially tell us. So perpendicular to the x-axis just means I'm slicing perpendicular to the x-axis. And then the cross sections are squares. So what that means is you can kind of think a square is coming up and out of the page at us. I tried to draw this picture a little bit, something similar at least, on Friday, where if I have, this is my x-axis coming out, my y-axis is going that way. Calc 3, you'll see this. My z-axis is then kind of going up. We don't need to label that z-axis, but just for pictorial sake, we have a circle in the xy plane. We are cutting up along the x-axis, and then that cross section is a square. So you can either way will kind of work. You can think of it as just all these cross sections coming straight out. Or you could kind of think of it how we did in the last problem as like the cross sections are sort of centered about that. I think either way should give us the same volume. It only works either way in this case just because it's a square. So let's draw this circle again. So we have some sort of slice. Let's do one in the back. Slicing perpendicular to the x-axis, and these cross sections are squares. So we're kind of attaching a square at every axis, and we're going to do this coming towards the x-axis and moving along the x-axis. And then the width then of these guys is a good thing to draw. So if the width, then what direction does it go in? On our picture here, since I'm slicing perpendicular to the x-axis, my width is dx. So any such pictures would work for this guy. So what is our integral? So our volume, generically, is the integral of dv. It is the sum of every infinitesimal slice of volumes we have. And well, what is the volumes of these guys? It's going to be the area of the base times the depth, if you want. So you can either write it as cross-sectional area times the depth. Kind of help point you in the right direction. The depth is easy, it's dx, and that tells us that what do I need for the cross-sectional area? I need to know a formula or a function for the area, and I need it to be in terms of x. So of course my area now that we want to pick out, they're squares, so it's just going to be, you know, length squared or width squared, whatever variable you want to use. Let's just use w. Kind of depends on which picture we use here. And so that's going to be essentially twice this length. So we are just given a circle of radius 2. A little bit of work to do here. What is the equation of a circle of radius 2? Is going to be this guy. Will give us the top part. Of course, the bottom is just going to give us the negative square root 4 minus x squared. And so the width, we could either model as top curve minus the bottom curve, or twice of half of it because of the symmetry. So again, just to kind of pick out all these pieces, volume was integral of dv. I know what my dv, by the way, we sliced it up, was just the cross-sectional area times dx. Okay, what is my area? Areas are squares. Squares have an area of width squared. And of course, now we figure out that the width is 2 times square root of 4 minus x squared, based on our functions in the shape of the region that we're creating these cross sections over. And then now we just fill it all in. So let's kind of continue this. Our volume is then the integral of 2 square root of 4 minus x squared squared, and then keep the dx hanging out there. The last thing, of course, we want to need, or we're going to need, is the bounds. We're integrating with respect to x, and so we are integrating from the left side all the way over to the right. And of course, since it's a circle of radius 2, we're just going to be integrating from minus 2 to 2. Everyone see that? What's the next one? I think that we use similar shape. Where'd that project go? Next one says we've got same thing as a base, circle of radius 2, centered about the origin. Cross sections are perpendicular to the x-axis, but now are equilateral triangles. So let's go through this thought process again. So same circle. I'm just going to say cross section. Equilateral triangles. So we've got our circle. And now, what are the cross sections? Equilateral triangles, but in this case, I think we have to assume that the base of the triangle is sitting at the bottom and the triangles are coming out top. So to try to draw a 3D picture again. We're taking cross sections perpendicular to the x-axis, and each cross section is a triangle. So our volume, integral of dV, which is the integral of the cross-sectional area. And again, because we are perpendicular to the x-axis, the width of those guys is going to be dx. So all of these cross-sections, this will always hold for all of these cross-sectional area ones. We change our method going from what is our dV to this, it's going to be maybe a little different, and it will change up once we get to work as well, of course. But it's always cross-sectional area times the infinitesimal piece, or the infinitesimal dimension, which is our depth, I guess, if you want to call it in this case. So what is our cross-sectional area? Is 1/2 base times height, since our cross sections are triangles. And so this tells us I need to figure out, well, what is the base, what is the height, and I need both of those in terms of x. So this triangle here, we can kind of see that the base is going to be there. So that's this piece. Actually, maybe I should start using some different colors. I don't know how well you guys can see that on the pictures. Sometimes when I think drawing the picture itself in a solid color and then putting all these annotations in maybe a lighter color might help see things. I don't know if I like that light blue. Let's use good old pink. So that's our base. And so what is the base? It's essentially twice the y. So we do have the same curve as y is equal to square root of 4 minus x squared. And the bottom one is, of course, negative 4 minus x squared. So the base is pretty easy. The base is just going to be 2 times square root of 4 minus x squared. Essentially the same base as our rectangles were in the last case, or our squares were. But in this case, instead of squares, I can't just take the base squared. Now I got to figure out the height. And so Got to remember all your geometry. And trigonometry. So if I have half the base, since I have an equilateral triangle, what is the height? So equilateral triangle has 60 degrees, which means we got a 30, 60, 90. And in a 30, 60, 90 triangle, the ratios are 1, 2, square root of 3. Which means that if I take half the base as the sort of lone small side, the height is then square root of 3 times that. So square root of 3 times 1/2 the base. In other words, we get square root of 3 times square root of 4 minus x squared. Everyone see that? Okay, so we've got all our pieces. Now let's just stick them in the integral. We had a dx. We've got our formula for the area. So now our volume is going to be the integral 1/2 times the base times the height. Everything's in terms of x. We've got our dx there. And then what are the bounds? So again, the bounds are the ranges. Since we're integrating with respect to x, the bounds is going to be just the numerical bounds of where are we ranging along the x-axis. So from -2 to 2 again. The bounds are only determined by the shape of the region, not by the cross-sectional information. So simplifying that, not too bad, -2 to 2. We've got that 1/2 and 2 are going to cancel. I've got a square root 3. It looks like the constant that's going to be hanging out. And then just 4 minus x squared dx. Square root goes away nicely. Any questions on that one? All right, let's take a look. I think there's 3 more. Let's try to move through these a little quickly. I don't know, maybe we'll skip some if I don't think it's too important. Cross sections are heights of rectangles. So the next one, they kind of give us almost all the information there. There's no geometry we have to work out, it looks like. So let me draw it out real quick. So the base is just vertices square, side length of 4 looks like, centered at the origin. So we've got our vertices at like 2, 2 and negative 2, 2 and all that. So we've got those 4 points. This is our region. And then cross sections. Height minus x squared plus 4. And they are rectangles. Perpendicular to x-axis. All right. So I just drew That's kind of my shorthand math for perpendicular, is just drawing two perpendicular lines, right? I'll put two parallel lines for parallel. I do that a lot in pre-calc. So what's going on here? We're still perpendicular to the x-axis. We're creating rectangles though, and the height of the rectangle that's coming upward is given by this function. So if you want to try to draw a 3D picture, let me try to just do it real quick. Yeah, getting a little too fast. We've got our x and y. We're taking cross sections here. The base we know, it's pretty clear. Then the height of these rectangles is given by minus x squared plus 4. And of course, the depth is our dx. Going out like that. So this one's not too bad. Volume, dv, adx, base times height for the area. And what is the base? So if our base is this piece, it's always going to be 4. What is the height? They give us the height, minus x squared plus 4. And then the bounds. Bounds are where are we integrating along the x-axis? Minus 2 to 2. So nothing fancy with that guy. What's the next one? Let's see, we got a couple more. Region enclosed by a couple of curves, cross-section perpendicular to the y-axis. In this case are squares. And then in the last one, we've got a parabolic zone. Our right isosceles triangle. So it doesn't look like we've done cross-sections of semicircles. That one also comes up quite a bit. Maybe we can just try to throw one in here. Let's see, we've got about 30 minutes left. So base, cross-section is perpendicular to the y-axis. Let me do the fourth one. The fifth one, maybe I'll leave to you guys to check out. I do kind of want to get to a couple of the homework problems just to get you guys started and maybe touch on this shell method before we get into it tomorrow. So just to do one perpendicular to the y-axis, they give us y equals x squared and y equals 3. So we've got y equals x squared, y equals 3. So this is our region here. Cross sections are perpendicular to the y-axis are squares. So again, we've kind of got squares coming out above this. And because we are perpendicular to the y-axis, the depth of these squares is going to be dy. So my volume so my area and my differential now is dy. So I need area in terms of y. So if that's y equals x squared, that means if I solve for x, x equals square root of y. And since they are squares, area is pretty easy. We just need to figure out the width, and the width is this distance. It's just x. And of course, we need that in terms of y, so my width is just square root of y. Volume then is square root of y squared dy. And then the bounds for y, 0 to 3. Okay, so the last one's a little trickier again. Base is parabolic region, and cross sections are right isosceles triangles. So try to figure that out. It's a little bit more geometric than some of these other ones. So there's a bit more to do to try to figure out right isosceles triangles. Not too difficult though. It actually might actually be easier than the equilateral triangles, because equilateral triangles you have to cut in half. Right isosceles triangles are already right triangles, so you can use kind of your trig to figure out, what are the ratios of the side lengths and all that. And since they're right isosceles triangles, it's a 45, 45, 90 triangle. Okay, so let's talk about this homework problem. So if you want to pull up the homework assignment, look at the last one, number 11. So homework 4, number 11. What's it say? It just says a wedge is cut out of a circular cylinder of radius 4 by 2 planes. One plane perpendicular to the axis of the cylinder. The other intersects the first at an angle of 30 degrees along a diameter of the cylinder. Find the volume of the wedge. So let's draw the picture. It's a little hard to think out. So let's just take each piece at a time. We've got a cylinder. The first piece just says one wedge is cut perpendicular to the axis. So we can kind of just think of that as the base. Base of this wedge was just, we need a flat bottom perpendicular to the axis. And then what's happening is that another wedge or another plane is intersecting this at a 30-degree angle relative to a diameter. So if we kind of dot a diameter there across, then there's going to be a plane cut this way. So this is our wedge. But it's got this kind of weird cylindrical shape almost to it, or that it's being cut out. So I know that that was 30 degrees. And now what we need to do is find the volume of this. So if you can kind of imagine the shape of this guy, it's a wedge. Looks kind of like a door stopper. But if we kind of looked at this slanted surface, it would be like this stretched kind of, it would be an ellipse there in that direction. So how do we find the volume of this? So any ideas? It's going to be a cross-sectional area. We just need to figure out, well, how should we take our cross sections? So what's the giveaway that we should do cross sections? Well, we started off with a cylinder, which we like rotating things if we're doing these washer disc methods. But if you look at the shape itself, it's not symmetric, right? It's not like a rotated shape. It's a sliced shape. So we're going to need cross sections. And you have a little bit of freedom here of how to do this. Any thoughts? So, what'd you say?
Use the triangle shape?
use triangle shape, that'll work. The other thing that might work is we could either slice vertically or along the x-axis. So let's kind of, I don't know how we want to model this here. Let's model it this way. So let's kind of draw it with our standard coordinate plane, where this was our y-axis, this was our x-axis. Then upward is our z-axis. So if you're not sure, kind of go through and just try to think of the geometry of how do I want to slice it up? And then what axis do I want to be perpendicular to? So if we slice it going into the page, you might kind of think that can work, because if I slice a cylinder horizontally, it'll give me circles, but because of the shape, if I slice horizontally, it won't give you nice circles or nice shapes. Because we already have this right triangle, though, if I slice perpendicular to the x-axis and go forward and backward with my slices, so in some sense I'm slicing in planes parallel to the y-axis up and down, then I'm going to get these right triangles. So this was actually similar to the problem that the last problem on that activity that we didn't do. The other thing you might try to do is if I slice vertically, but now perpendicular to the y-axis, so my planes are going inward and I'm cutting left and right, then we could get rectangles out of that of varying heights. So let's do slice perpendicular to the x-axis with vertical slices. Which gives us cross sections of right triangles. Okay, so let's draw a different picture here and try to pick some of this out. We've got this circular base. The pictures are getting a little sloppy, sorry. And well, there's one right across the middle is a nice right triangle. And you can kind of see that if I slice at any other point, we will still have a right triangle. It's just that what is changing, the width is going to change and the height will change as well. So my volume the differentials are dx, since we're slicing perpendicular to the x-axis. And now what is the area? 1/2 base times height. And now we just need to figure out, well, what is the base and what is the height? Base is pretty easy. So since it's a circle, again, we can model this function. This is probably new to a lot of you guys, at least the way we're orienting it, because x is coming out at us and you're used to seeing x horizontal, but it's still just a circular base. So it's still just square root of, what was the radius? I think the radius was 4, wasn't it? So 16 minus y squared is that function. And my base should then be 2 times square root of 16 minus y squared. The height you can get from trig. So you just have to remember your 30, 60, 90 triangles. I don't know how it was taught to you, but the way I teach it in pre-calc, it's easiest just to remember the ratios. The hard numbers don't matter because every right triangle that's a 30, 60, 90 triangle is similar. So the ratios of sides are going to be the same. So the way I remember it is just 1, 2, square root 3. Short side's 1, hypotenuse is 2, long side, and then the other side, square root of 3. That's our pi over 3, or excuse me, pi over 6, 30 degrees, and our pi over 3 side there. And so what does our triangle look like? Well, if this is my base, is 2 times square root of 16 minus y squared. That's that guy. That means the ratio of the height to the base is our tangent ratio, essentially, of this side of our 30 degrees, should be 1 over square root of 3. And so we can fill that in. I don't know the height, but I knew the base was 2 square root of 16 minus y squared. And so what is the height? 2 over square root of 3 times square root of 16 minus y squared. Everyone see how I got that? So just remembering all your trig, how to solve all your trig problems. We didn't even need, I guess, trig for that. Really just ratios of similar triangles. And if you want, you can rationalize the denominator. I'm not going to worry about it. And if you want to, it's one of those things that might simplify in the problem depending on what else comes up and what the functions are. And it might be one of those things that just goes away at the end, or you can always just rationalize it at the end. One of those things also, like on a multiple choice test, sometimes like if there's constants involved that they're not, they rationalize all the denominators, it's something you're going to have to do. Okay, so let's just go ahead and fill in everything now. So our area was 1/2 base times height, which means our volume is 1/2 the base, 2 squared is 16 minus y squared times the height, which is 2 over square root of 3. Square root of 16 minus y squared. Why did I put y's in there? I need x's. No one checked in on that. My brain's being dyslexic today. Y equals 16 minus x squared. I probably just misread my own writing. That happens. I've seen students do that. Sometimes you don't make your x enough and it looks like a y, and then all of a sudden you're writing y's. And then our dx. And then, yeah, just simplify. So let's see, the 1/2 will cancel. The square roots will go away nicely. Looks like our constant is still going to be a 2 over square root of 3. And then the function 16 minus x squared dx. Bounds are the x bounds. So we're cutting up along the x-axis. Sorry, front and back. And so the bounds were -4 to 4, since that circular region we're over is a radius 4 circle. Any questions on that guy? Anyone still writing or anything? All right. So we got about 15 minutes. Let me introduce the shell method. And so what we have for the shell method, let's suppose we're back to this rotation volumes of rotation. And I've got my function now is something like 2x squared minus x cubed rotated about the y-axis. Functions that, I guess we should say y equals 0. And then it's a region between those two curves. So if I'm bounded between these two curves, I'm not given the x bounds. We actually need to solve for them. So of course, the intersection, I would just set those two equal to each other, which is nice enough, just finding the zeros of that polynomial. And what do we get? 0 and 2. So this region looks, we've got an intersection at 0. I guess I should say, I mean, x bigger or equal to 0. That's not going to matter too much. It's kind of a symmetric polynomial, but it's going to kind of slowly gradual get up and then come back down here at 2. So we're looking for this region, and then it's rotated. So something like that. My humps are not quite the same size. And so what's our problem here? Well, if we were to do this with our traditional methods that we've learned so far, we would have to do a washer method. Okay, well, that's fine. At the moment, it looks all right. Our washer method, though, our differential height is dy. So we're going through our problem-solving methods. Okay, my width of these washers is dy. I need all my functions in terms of y, which means I need the radius of this in terms of y. Okay, well, that's a little weird now because this function was just one function. But if we do it this way, we see we clearly have an inside radius and we clearly have an outside radius. So I somehow need to find and solve this guy for x. So to use washers, we would need to solve this equation for the two functions of y, i.e. solve for x. So functions in terms of y. And that's our problem, because it would be split, right? We need one function, and then somehow it would split. And then we'd have this other function when we're looking, kind of just looking at it sideways, right? Now, if this is my independent variable, I need this part of the function and then this part of the function. But we don't have a way of doing that, right? Look at this function. How do I solve that guy for, solve for x? It's x squared minus x cubed. I can't just take a square root or take a cube root because I'm adding two of those separate powers together and I can't kind of isolate any of those. There's no way I can solve only in terms of x. So we can't do that. So what do we do instead? Instead, we need a new shape. And what is our shape going to be? Instead of these washers, what we're going to do is now consider cylinders. So what we're going to do is now think, well, if I have a cylindrical shell. So again, this is kind of a big kind of engineering type thing that you might see in like a CAD program, where now the width, so think of it like a can, you know, like just a regular soup can, except no top, no bottom. It's just a soup can, and the width of the can is really thin. It's just dx. And so really all it is a cylinder, and it's like the shell of the cylinder, which is why we call it the cylindrical shell method with this tiny width. And then what we're going to do is keep expanding these shells outward. So like over here, I have another cylindrical shell. Let me draw it in a different color. And so we're kind of just taking all these cans of shells and then kind of stacking them right on top or right next to each other. You can almost kind of think of it like those, like, what do they call those Russian dolls that kind of keep fitting in each other? Except just kind of consider it as these cans that each time you stick a can inside each other, they kind of all stack together. Almost like one of those like extendable, what are they, like the extendable lightsaber toys where you kind of flick it and then all the cylinders kind of catch on to each other. So they're all really, really close to together. And if I kind of add up the infinitesimal volume of each of these shells, then we should get the volume of everything. Okay, well, so let's write out our generic statements. Volume is just the infinitesimal, the sum of all of the infinitesimal pieces of volume. Okay, well, what is our infinitesimal piece of volume? Our infinitesimal piece of volume is the volume of one of these shells. Well, one of these shells, it's the area of the cylinder times essentially just times the width of it, the thickness of the cylinder. So in this case, this is the area of the shell. You can kind of think of it as like the surface area of a cylinder, right? It's just that outside, that broad outside shell. And then we don't have a top or a bottom, so I don't need to worry about those components. And so you just have to remember, well, how do I find that? The area or the piece of the surface area of a cylinder, it's going to be the total length that we traverse around the base, the circumference, times the height, which is 2 pi r h. Okay, good. So we've got all of our geometry there. Let's now make sure that all the variables match with what we want. Well, the height is pretty easy. What is the height of this guy? It's given by the function. It's just the y value. So my height is just 2x squared minus x cubed. What's the radius of these guys? Now you got to be careful with the radius, especially if we're not rotating about one of the coordinate axes. In this case, we are rotating about the y-axis. So the radius, remember, is going to go, let's see, what colors do I got? Let's use orange. It's going to go from the y-axis out to there. What is that? That is whatever x value we are at. So my radius is just x. I don't know if that diagram's getting too cluttered there. So let's just write it. The radius is x. The radius is whatever x value we're at, right? The way we're doing this is we're slicing up the x value, and whatever x value we're at, well, that is the radius, and the height based on that x value is given by that function. So now we have all of the pieces. We can just put them in. Our area was 2 pi times the radius times the height. And all that worked out much nicely, right? Much more nicely. We didn't have to solve for y's in terms of these complicated functions. Even if I could have done the washer method, sometimes it's almost easier to do it this way, because especially if the functions are already solved in terms of y in terms of x, well then my radius almost always just gives me an extra power of x. Constant's a little different, and the height is pretty easy to solve for. Geometrically, though, sometimes this can be kind of hard to see. Sometimes it's a little harder for students to kind of see how that fits in using these shells. It's not as kind of easy to see these washers. And so the last thing we need is just our bounds. Our bounds are in terms of x. Where do our x values lie? Well, the smallest radius is going to be 0. The biggest radius is going to be up to this other intersection point here, which we found was x equals 2. So integral from 0 to 2 of that guy. So nothing too tricky there. I'll leave you guys to finish it. So 2x cubed minus x to the 4th dx. Pretty basic integral after that. Any questions? We'll do more of these tomorrow. I think there's a project tomorrow as well that we can start practicing all these guys. And I'll have office hours tomorrow again to help you guys with your homeworks if you need to. I'm going to go ahead and stop the recording.